Let's Boltzmann Q A, how to implement a do-nothing boundary condition. So this actually comes from the homework of some of you. It was not in the lecture, but some of you took this somewhere from the internet, and so I thought I'd make a video about this. So first of all, boundary conditions in the lattice-Boltzmann method in general. So if we compare this to how we implement boundary conditions in the Navier-Stokes equation, we usually have there these primitive variables velocity and pressure. And in the lattice-Boltzmann method, we have to impose the populations Fi and J instead, which, depending on the orientation of the boundary, could either be more variables than velocity and pressure or less variables than velocity and pressure. So what we observe in the practice or in the literature in lattice-Boltzmann, we usually do not distinguish boundary conditions in the way it is usually done for partial differential equations, where we say set Dirichlet or Neumann boundary condition. We rather set the boundary conditions according to what they are physically meaning. For example, we have no slip boundary conditions, that would be the bounce back, or we would have slip boundary conditions which were not introduced in the lecture, that would be done by the bounce forward method, for example. And what we are actually trying to do in this short video is to actually introduce outflow boundary conditions. So at the outflow in the Navier-Stokes equation, you would have the possibility to set a pressure boundary condition, for example, zero pressure at the outlet. This can also be implemented in the lattice-Boltzmann method, for example, with the anti-bounce back method, which again we did not have in the lecture, or also by the do nothing, which is an extrapolation boundary condition. So first of all, what do we mean by do nothing, and what would we actually like to obtain? Let's just look at a simple flow condition where we have an inflow on the left-hand side, an object, and then we have a wake. And this wake would usually continue forever, but of course we have finite resources, so we cut our domain just somewhere, and in this position we would like for the flow to just continue. Yeah. So only the black part and the green vortices, they are simulated, and at the outflow, what we would like to do is to just extrapolate from the flow field inside the domain to a flow field outside the domain. And this we define as our outflow. So we do not want to specify anything, no velocity and no pressure. Everything should develop by itself, just by extrapolation. And this can be easily implemented in the lattice-Boltzmann method. If we look at the characteristic diagram, what we can do is, if we have a boundary, say here's the end of our domain, so then we have a boundary condition at the position xbc. This is where we have our last node. And this last node is missing in one dimension one of its entering populations, or in 2 dimensions it would miss 3 populations. Now, and what we now very simply do is we take the pre-collision state from the neighboring node and copy this. So from the first node inside the domain, and copy this to the outlet, or to, in that case, it is supposed to be an outlet, so it is at the position where the physical flow leaves, but it is the position where we have a missing distribution, and so we get this missing distribution just by copying it from the neighboring node. And this is supposed to be zero order extrapolation. So now this is the equation that we can apply. So we have the population that is going in opposite direction from the outlet, which we identify with Fi bar at the boundary, is simply the distribution at the same time step at the neighboring nodes in negative x direction. So now this characteristic diagram is always only valid for one dimension. If we have it, for example, in 2 dimensions, what we do, we copy all the 3 distributions from the same node, one grid spacing inside the domain to the node at the end of the domain. Okay, so this is quite simple, and this is what some of you implemented in your homework. Now, is this a good thing? Well, this has some shortcomings. For example, it does not specify the pressure, and the pressure needs to be specified somewhere in the domain. Otherwise, the pressure could get to any value, and so if it could also go to negative values or to 0, and this could crash your code. So you have to fix your pressure somewhere in the domain, and if you don't fix it at the outlet, you have to fix it at the inlet. The next thing is that this is only a 0 order extrapolation. So what we do is because we just copy the distributions, yeah, we do not actually have a continuation of any curvature in the flow, like when we have a vortex. Yeah, so this is also not very accurate, and it is, and the thing that is probably the biggest problem is that it's not non-reflective. And this is what we briefly look at here. Why is this non-reflective, and what do I mean with non-reflection? So in the lattice-Boltzmann method, because we have an weakly compressible solver, we have sound waves in the domain, which is now indicated here. For example, if this is the node from which we copy our distributions, and there is a pressure wave at this position, then this pressure, according to the usual values in the lattice-Boltzmann method, would move 1/1/3 grid spacing in one time step. So it will not move, so a pressure wave will not move to the next node, but it will only move to 1/√3 part of the node. So it will arrive basically here in this position. So what happens if we copy the distribution from the node here to here is that we also copy the pressure wave, and this pressure wave that we copied will now enter the domain in this position here. So we introduce a spurious pressure wave, and this spurious pressure wave is, of course, coming as a reflection on the boundary. So there is, of course, a way to solve this, and this you find in the cumulant lattice-Boltzmann paper in one of the appendices. We can redefine this boundary condition as a non-reflective boundary condition by a relatively simple trick. So what we have to do is we have to just copy our distribution from the position where the pressure wave would come from, that is on the where the pressure wave at the outlet would come from. So the pressure wave at the outlet would move with the usual speed. So it would have the Cs equal to 1 over square root 3 delta x by delta t. So it would come from 1 over square root 3 delta x delta t inside the domain. So the problem here is that there is no node here. And because there is no node here, what we have to do is we have to do an interpolation between the node next to the boundary and the node at the boundary. And then we have to write this back at the next time step. So this leads to the following interpolation, which we see here. So we take the distribution or the population at the neighboring node at the previous time step. We have to multiply this by the weight 1 over square root 3, and we take the distribution at the boundary in the previous time step and have to multiply this by 1 minus 1 over square root 3, and thus we write back to the next time step. And with this boundary condition we killed the reflection, but we still are only low order accurate in our interpolation. So this is what I want to say about the do-nothing boundary conditions. I will link the paper where it is described in the descriptions. Thank you for listening.